I spent roughly $100 building these panels, and they're performing just as well as the commercial ones that cost upwards of $1,000. Welcome back, guys. Today, we're exploring the world of solar air heaters. You can use these for a ton of different applications, from keeping your home warm to drying out crops or making dehydrated food. And after that, I'm going to walk you through the entire journey of constructing a few budget-friendly, simple DIY solar collectors. We will put them head-to-head to see which layout gives us the best bang for our buck. Think of solar collectors as solar panels, but instead of making electricity, they generate heat. The crazy part is how incredibly efficient they can get. Standard commercial electrical panels usually peak around 22 or 23% efficiency, but a properly built solar air heater, those can reach 70 or even 80%. That gives you way more practical energy from the exact same sunlight and the exact same footprint. To start, we'll cover the basic science and physics behind the scenes. Then, I'll put together 5 distinct homemade designs. I'll test them all side by side to find the ultimate, most cost-effective blueprint for an easy DIY solar heater. Oh, and a quick note, we are strictly focusing on heating air today. Heating water is a whole other beast, and I'll cover that in a future video, since the design choices are pretty vastly different. And don't forget, if you want some personalized advice on a project, you can always book a consultation through my website, which is linked in the description. All right, this is a massive subject, and we have a ton to unpack, so let's get right to it. The first step is understanding how heat actually travels. There's some nuance to this, but generally, heat transfers in 3 main ways: radiation, conduction, and convection. First up is radiation. This happens when heat moves through empty space as electromagnetic waves, like how the sun heats our planet. Picture it as invisible light that you feel on your skin rather than see with your eyes. Then we have conduction. This is heat transferring through direct physical contact, passing from atom to atom inside a material. It's the reason a hot frying pan's handle will eventually get hot enough to burn your hand. Finally, there's convection, which is heat moving from place to place via a flowing fluid. And keep in mind, fluids mean both liquids and gases here. The classic example is warm air rising. As air heats up, it expands and gets less dense. The cooler, heavier air around it sinks down, forcing that warm air upward. If your heat source keeps running, it warms the incoming cooler air, pushing that up too, creating an endless loop. We call this a continuous convection current, and it's exactly what drives ocean currents and makes chimneys work. So that is how heat moves. Now let's tie those concepts to our solar air heaters. Step 1 is finding a great absorber material to trap as much of the sun's energy as possible. We need a material that is fantastic at soaking up solar radiation. Then, we engineer an airflow path to sweep across that absorber. Convection then steps in to efficiently pull the heat off the material and carry it away into the moving airstream so it can be delivered wherever you need it. We also need our absorber to be highly conductive. If our airflow isn't perfectly uniform, good conduction prevents hot and cold patches from forming, which would drag down the overall efficiency of the panel. Put simply, we have a panel that we aim at the sun, and we blow air over it to grab the heat. When we're dreaming up these designs in the theory stage, one crucial concept is stagnation temperature. This is the absolute maximum temperature a panel can hit under any given weather conditions if the fans are turned off and no air is flowing. Basically, it's the total solar energy absorbed minus whatever heat escapes back into the outside environment. We want that stagnation temperature to be as high as possible because it's a key variable that helps us pull the maximum usable heat out of the system. To get there, we rely on materials like insulation and clear glazing to block waste heat from escaping. Just to throw some imaginary numbers out there for context, a panel without a clear cover might stagnate around 50 degrees Celsius on a bright summer day. Add a clear glazed cover, and that exact same panel might stagnate closer to 100 degrees Celsius. Once the basics of panel design are covered, we have to think about what we're actually using the heat for. The 2 biggest factors to consider are your target temperature and your required airflow. Different jobs need different temperatures. Keeping a house warm in winter requires relatively low temperature air. Drying crops takes a mid-level heat, and dehydrating food requires much hotter air. Airflow needs change drastically depending on the job, too. Heating a large 5-bedroom house requires massively more moving air than warming up a tiny off-grid cabin. So, this roughly splits into 2 main buckets: high temperature with low flow, or low temperature with high flow. And naturally, solar air collectors already balance themselves this way. If you pump air through the collector really fast, it has less time to soak up heat. By cranking up the airflow, you inherently drop the exit temperature. And of course, we can tweak the physical design of the collector to favor one outcome over the other. It is also worth mentioning that the cooler the inside of the collector runs, the more mathematically efficient it can theoretically be. That's because as internal temperatures rise, the heat lost to the outside world also rises. This brings us to a major distinction. Optimizing for solar efficiency is not the exact same thing as optimizing for your specific application. We definitely want a good, efficient solar collector, but application efficiency asks a slightly different question. It doesn't ask what percentage of solar energy we trapped, but rather, how much actual useful work did that hot output air accomplish for the cost? And answering that might lead you to make totally different choices regarding materials, panel shape, or fan speeds. Here is a quick example of what 2 theoretical panels might give you. A high-flow setup pumping out 3-4 degree air might run at 78% efficiency. That's fantastic for warming up a living room, but it would be pretty useless for drying anything out. On the flip side, a slow-flow setup pushing out 6-7 degrees Celsius air might only hit 61% efficiency. That would be brilliant for a dehydrator, but nowhere near optimal for home space heating. Okay, that covers a solid chunk of the theory behind solar collectors. Now, let's look at the physics of our physical design choices. One of the absolute most critical concepts to grasp is boundary layers, because they have the biggest impact on heat transfer. A boundary layer is a super thin sheet of fluid right against a surface, where the speed of the fluid shifts from 0 right at the surface up to the full speed of the main fluid flow. At the exact surface level, fluid molecules are basically glued in place because of friction. We call this the no-slip condition. As you move slightly away from the surface, the speed ramps up until it matches the main airstream. The reason this matters so much for moving heat is that this slow, sticky layer of air acts like a thermal blanket. Heat trying to jump from the hot surface into the moving fluid has to fight its way through this sluggish boundary layer via conduction, rather than convection. And because air is a terrible conductor, this layer acts as a massive roadblock. So, our goal is always to shrink or break up that boundary layer to boost efficiency. As we start the actual builds, keep in mind that the physical shape of the collector tweaks a bunch of variables all at the exact same time. Airspeed, turbulence, pressure drops, the thickness of that boundary layer, and how evenly the air spreads across the absorber, just to name a handful. The frustrating part is that fixing a design to improve one or two of these things usually makes the others worse. Take a basic backpass collector, for instance. Just tweaking the depth of the air gap behind the absorber metal changes everything. A really shallow gap creates fast-moving air and better heat transfer, but it makes it harder to push the air through, meaning a bigger pressure drop. You'll need a stronger, power-hungry fan to force the air through. A deeper gap slows the air down, which might give you hotter air and reduces the pressure drop, but your convection takes a hit, and you risk creating dead spots where the air just stalls. You could add baffles inside the gap to stir up turbulence, destroy the boundary layer, and increase heat transfer. But that makes it even harder to push the air through, again requiring more fan power, and risking even more dead pockets where the air refuses to move. That is the harsh reality of designing these. Every single choice is a compromise with pros and cons, and you have to decide which factors matter most for what you are trying to achieve. All right, enough of the classroom theory. Let's get to building. To set the stage here, I'm putting together 5 distinct layouts. However, they will all share the exact same absorber dimensions, and use the exact same fan setup. Doing it this way ensures we get the fairest apples-to-apples comparison possible. I should also mention that there are so many moving parts here that, in a perfect world, you would need to build hundreds of these boxes to truly crown the absolute most efficient winner. Tweaking just one tiny detail can completely flip the results. For this experiment, I am just aiming to build the best possible versions of 5 specific layouts, all while keeping them cheap and easy enough for anyone to build at home. Let's start by prepping the materials and going over what I chose. For the clear cover, or glazing, I am going with this twin-wall polycarbonate plastic. It isn't quite as perfectly see-through as glass or acrylic, meaning we lose a tiny bit of light coming in. However, it holds heat much better, weighs practically nothing, and is very affordable. Overall, I feel it is the smartest middle ground option. Of course, if you were chasing pure theoretical perfection, you'd likely opt for heavy, double-paned glass. For the heat absorbers in most of these boxes, I selected standard ribbed roofing steel. It is super easy to find, fairly cheap, and conducts heat well. Plus, those ridges make it structurally strong and add extra surface area, which helps transfer more heat. I will spray this steel with a high-heat, matte black paint. The flat black finish ensures it soaks in the maximum amount of solar radiation, while the high heat rating prevents it from flaking off down the road. You can actually buy fancy specialty paints that absorb slightly more light, but the price tag usually isn't worth it for a backyard project. For keeping the heat in, all these units will rely on standard EPS, or expanded polystyrene foam board. Its thermal rating is not the absolute highest on the market, but it is extremely cheap, easy to source, and won't get ruined by water. Plus, you can always just stack thicker pieces if you want more insulation. The only reason I would splurge on the expensive stuff is if I was severely limited on space and needed a super thin box. For the framing, I am just using standard wood, cutting down some basic 1x boards. Now, for testing purposes, I'm simply assembling everything with tape. This lets me quickly rip them apart and make tweaks if needed. But if I were building this for a permanent setup, I would definitely use construction adhesive and expanding foam to lock it all together. Our very first layout is a basic backpass design. This is literally just a piece of the metal roofing with an air gap behind it, backed by foam insulation. Air gets sucked in at the bottom, travels upward through that rear gap behind the metal, and gets pulled out through a fan hole at the very top. I am leaving this one totally uncovered, with no clear plastic on front. This will act as our baseline control for the absolute cheapest and easiest build, and it will clearly show us exactly how much a glazed cover actually helps. I will kick things off by throwing a sheet of the foam flat on the table, followed by laying the wooden frame right over it. Then I just secure the corners with screws. Down here is the bottom edge, and you might see that this specific piece of wood is thinner than the rest. This creates a slit right across the bottom, which is our air intake. It lets the air pull in uniformly across the whole width of the box, and the opening is slightly larger in total area compared to our exhaust hole. Next, I'm securing the wood to the foam using tape. Like I mentioned, if this was staying on my roof forever, I'd run a thick bead of expanding foam right here to lock it down. It acts as a great glue and seals up any tiny air leaks between the wood and the insulation. But for our experiment, tape is fine, just making sure I don't accidentally seal over the intake gap. Up at the top, I have my exhaust fan ready. I need a perfectly sized hole dead in the middle for it, and this random can I found happens to be the exact diameter I need. I'll trace that as a guide right in the center. Grab a simple hand saw, slide this to the edge of the table, and carve out the circle. Next, the black metal sheet just drops directly on top of the wood. Once again, I am taping the perimeter down for the test, whereas a permanent build would get heavy-duty construction glue here. The final step is just wrapping the side walls and top edge with extra foam strips. And there we have it. The backpass unit is fully assembled. I will attach the fans to all of these later on when we set up the testing rig. I'll push this to the side and move on to design number 2. Panel number 2 is a front pass configuration. It is structurally very close to the first one, But this time the metal plate rests directly against the foam backing. The hollow air channel sits in front of the metal, and then a clear plastic sheet covers the whole thing. The mechanics are basically identical to the first build, but thanks to that clear cover, we should see a drastically higher stagnation temperature, and cold winds won't be able to steal our heat. The airflow path remains the same, pulling from the bottom, traveling up the channel, and exhausting out the top rear. Starting off the same way, I throw down a foam base. Then, I put 2 thin strips of wood down the left and right sides and tape them securely. These 2 pieces act as ledges to hold the edges of our metal sheet flat. Once the metal is placed, I build a complete wooden frame resting right on top of it. Just like our previous box, the bottom piece of this top frame is narrower, leaving an open slot for our air intake. I should point out the empty spaces created by the metal ridges sitting against the flat foam. These little tunnels will just be trapped pockets of air that will heat up. When we first turn the fan on, it will take a few minutes for those pockets to get warm. Because of that, this panel might look a bit lazy right out of the gate, but once that trapped air gets hot, it will basically serve as a thermal barrier, like hot insulation. It's entirely possible this actually boosts the final efficiency. Time will tell, but I doubt having trapped air behind the steel is a bad thing, especially since there are several inches of foam behind it. It's just going to act as a warm pocket of stagnant air. Next, I'll mark and cut the exhaust port for our fan, slicing right through the rear foam board. To block off the top edge where the metal meets the foam, I'll push a strip of insulation firmly against it and seal the joint tightly. I'm choosing foil tape for this spot, and I'll quickly hit the shiny silver part with black paint so it absorbs sunlight. Okay, time to seal it shut. I want to ensure no sawdust or trash is trapped inside, so I will give the metal a quick wipe down. Finally, the clear polycarbonate goes right onto the top wood frame. I will pull off the protective plastic film it comes on both sides, and I already stripped the bottom face. Tape the clear cover down tightly, wrap the exterior edges with our foam chunks, and seal the backside. That marks panel number 2 completely finished. Let's hit number 3. Our third project is a double pass system, which is a hybrid of the front and back layouts. It closely resembles the front pass setup, but it adds a second empty gap between the metal sheet and the back foam. The plan is for the air to travel down one channel, spin around, and travel back through the second channel. This forces the air to spend double the time inside the hot box. Material-wise, this uses practically the exact same stuff as the second panel, just requiring a tiny bit more foam around the edges. So, the price tag is effectively identical, but the goal is that adding this extra airflow path gives us a meaningful bump in performance. For the air route, I am setting the intake at the top of the front channel. The air will move downward against the plastic cover, curve around the bottom edge of the metal, and travel upward behind the steel plate. You could easily flip this flow direction, which would undoubtedly change the numbers, and that is a test worth running someday. While designing this, I went back and forth on which way the air should travel, and here is my logic. The air is going to reach its maximum temperature at the very end of its journey inside the box. The rear channel is entirely encased in thick foam. Therefore, putting the absolute hottest air in the most insulated section prevents heat from bleeding out into the cold air. The counter-argument for reversing the flow is that the front space right under the sun likely hits the highest absolute temperatures. So, if you warm the air up in the rear first, and then push it into the super hot front area right before it leaves, you might score higher final temps. However, the front area bleeds heat way faster because it isn't wrapped in foam. As the internal air gets hotter, the temperature gap between the inside and the outside weather gets wider, which accelerates heat loss. If your hottest air is in the poorly insulated front gap, you lose more energy. The clear plastic cover is essentially our insulation weak link here. If we were using extreme double-pane glass, running the air front to back might actually win. But with this cheap plastic, exhausting from the foamed-in rear feels like the smarter play. We'll have to experiment with that another time. Regardless, let's put together panel 3. Same drill. flat foam board first, followed by a wooden perimeter. I will carve out the rear exhaust port next, and secure the wood with tape. Notice that the metal sheet for this one is cut slightly shorter than the frame. This creates a small gap at the bottom edge, providing a tunnel for the air to wrap around from the front to the back. A second wooden frame stacks right on top of the metal. I'm leaving the bottom piece off this top frame entirely. It will just be sealed by the side insulation so the air has room to make its U-turn. Up at the top edge, we use a thinner strip of wood to create our intake slot. Once I tape this upper frame securely, I will wipe down the metal surface one last time and then apply the clear plastic cover. I'll wrap the backside with more tape, and that wraps up the double pass unit. Okay, so our fourth layout takes a totally different approach. This is known as a transpired collector. It looks pretty similar to the double pass unit we just finished, but the metal plate is completely covered in thousands of tiny holes. Instead of the air traveling down one channel and up the other, the air comes in through the clear front, passes directly through all those little holes, and goes into the rear channel. This specific plate has around 3,000 holes, which I painstakingly drilled by hand over a couple of hours. Getting paint on this thing is a bit of a challenge. You could start with pre-painted metal, but it gets pretty scratched up during the drilling stage anyway, so a fresh coat is required. To avoid clogging the holes, I roll out the heavy excess paint onto a scrap piece of metal first. Once the roller is just lightly coated, I paint the perforated sheet, and then quickly use a blast of compressed air to clear out any paint that tried to block the holes. There are a handful of reasons why transpired designs can easily outperform the other styles, but the biggest factor is how it handles the boundary layer. By forcing the air to squeeze through those tiny openings, it violently breaks up that stagnant layer of air on the back of the metal. Every molecule of air gets pushed into direct contact with the hot steel. Another huge bonus is that the depth of the rear air channel is much less critical. With the front and back pass designs, you have to keep that gap very narrow to keep the air moving fast and the boundary layer thin. Transpired panels work on a different physical mechanic, so we don't have to worry about that. A deeper channel actually creates a nice, even pressure zone across the back, ensuring air pulls through all the holes equally, rather than taking a path of least resistance and leaving cold, dead zones. Keep in mind that the holes need to be small for this to work properly, and the total amount of open space changes based on your needs. Fewer holes for hot, slow-moving air, and more holes for warm, fast-moving air. Let's put this one together. Same routine. Foam base, wooden border. Then, the perforated metal goes down. All that drilling made the metal warp a little, so I'm securing it with a few roofing nails to keep it flat. In a permanent build, a heavy construction adhesive would easily hold it down. Next goes the tape, followed by the upper wooden frame to build the front airspace. I will wipe the metal clean one last time, wrap the outer edges in foam, and drop the clear cover on. That is the transpired panel officially done. The fifth and final build is basically a budget-friendly twist on the transpired concept. Instead of a drilled steel plate, I am swapping in 2 layers of black fiberglass bug screen, separated by a tiny gap. This is substantially cheaper and way faster to build. It probably won't reach the exact same efficiency as the metal version, but if it cuts the cost by 1/3 and saves hours of drilling, it is absolutely worth testing. It functions exactly the same way, but with a lot less physical mass and way more porosity. First up is the foam and the wood frame. I'll cut the exhaust port out and tape the frame securely. Then, I pull the first sheet of bug screen tight across the wood and tack it down. A second, thinner wooden frame goes on top as a spacer, followed by stretching the second layer of screen over that. Finally, the topmost frame gets added to hold the clear plastic. Looking at it now, the screen is so open that the bright white foam behind it really stands out. So, I'm going to pull this top frame off, spray paint that rear insulation flat black, and stick it back together. That quick extra step is going to absorb significantly more solar radiation. I'll slap the plastic glazing on top, and panel number 5 is in the books. Now it is time to prep our experiment. Let me walk you through how I am running this test and the gear I'm relying on. I am utilizing standard 1-2 volt PC fans to draw the air through each box. They are wired to a variable power bench supply, which lets me dial the voltage up or down to change how fast the fans spin. I'm going to test a few different fan speeds to observe how flow rates impact our final heat output. To track that speed, I have a digital anemometer. It is essentially a tiny, super-sensitive fan that I hold up to the exhaust, and it reads the air velocity. Using that speed and the size of the hole, I can calculate the total volume of air moving through. For the temperature data, I am using a custom Arduino logger I threw together for an older gasifier project. Just tweaked a bit for today. It features 5 separate temperature probes that sit inside the exhaust of each panel, logging the exact temperature every 2 seconds. By the end of the day, I will have a massive spreadsheet of data that I can graph out to see the real winners. The whole brain box runs off a standard power tool battery, so it is completely portable. Once I plug it in and tap the screen, it starts recording and gives me a live readout so I can watch the numbers climb in real time. To mount the fans, I just center them over the exhaust holes, make sure they are pulling air out, and drive long screws directly into the foam board. It's not bulletproof, but it is plenty strong for an afternoon of testing. A quick wrap of duct tape seals up the edges nicely. Okay, everything is plugged in and running. I have them lined up in the order we built them, 1 through 5. Right now, there is a tiny bit of shade clipping the bottom edges, so I am going to ignore the data until the sun fully clears the trees. But right off the bat, looking at the live numbers, something wild is happening. The cheap bug netting panel is actually running hotter than the drilled steel panel. That blew my mind. The screen is sitting at 62 degrees Celsius, while the metal one is at 59. They just booted up, so maybe the steel needs more time to soak up the heat. We will know for sure once the data logs for a while. Let's check our initial air speeds. Right now, they are all pulling about 3 meters per second. The temperatures are sitting at 34 degrees for the unglazed panel 1. Panel 2 is at 53, and panel 3 is at 54. Those two are structurally very similar, so neck and neck makes sense. Panel 4 is at 61, and panel 5 is at 63, so the bug screen is holding on to a slight lead. I'm going to let them bake for a few hours and log the data. Here is an awesome observation. A thick cloud just rolled over, and the temperature on the bug screen plummeted. It instantly dropped from 63 down to 43. Meanwhile, the metal transpired panel only dropped from 61 down to 56. That tells me the bug net can achieve incredibly high peaks under perfect sun, but the solid metal sheet acts like a thermal battery, keeping the heat steady when clouds pass by. Once the sun peaked back out, the screen shot right back up to 65, while the metal held steady at 61. It is fascinating how differently they react. It is also quite breezy out here today, which is rapidly stripping the heat away from our first unglazed panel. It is hovering at 35 degrees, while its glazed twin right next to it is at 56. That visually proves exactly why you need a clear cover on these things to trap the heat. I'm going to dial the power supply down to 9 volts now to slow the fans down, take fresh airflow readings, and let the logger do its thing. All right, day 2 of our experiment. I wanted to run a second test under completely overcast skies, because you aren't always going to have flawless sunny weather. Real quick, if you are enjoying this, hitting the like and subscribe buttons goes a massive way in helping us out. I read all the comments, and you guys always have great insights. The boxes have been sitting outside for an hour while I set up the wires, so they have reached their max stagnation temperatures for a cloudy day. I'm going to run the exact same routine, cycling through different fan speeds to see how they handle low light. While they run, I brought out a thermal camera to check our foam jobs for any major heat leaks. The black duct tape is definitely showing up warm on the screen, but around the actual wooden corners, everything looks tight. The foam is doing a great job, and a bead of construction adhesive would only make it better. I've finally had time to comb through the massive pile of data, and the results are incredible. For roughly $100 a box, I am hitting performance numbers that easily rival commercial units, costing over $1,000. I charted all the temperatures and calculated the raw power outputs, and I have some major takeaways. Looking at the timeline graph for the Sunny test, you can watch the different panels climb and fall as I changed the fan speeds. Obviously, passing clouds cause some messy spikes in the data that I can't control for, but the overall trends are undeniable. First off, a clear cover is non-negotiable. The open-faced back-pass panel lost by a landslide in every single metric. Surprisingly, there was practically zero difference between the front pass and the double pass designs. This is where one tiny variable might have changed everything. Maybe my fan speeds were in the wrong bracket, or maybe the air needed to flow front to back. But as built today, the extra channel was just wasted effort. The true champions were the metal transpired and the bug screen panels. They absolutely crushed the other designs, and remarkably, the bug screen beat the drilled steel almost all day. The screen reacts instantly to sunlight, while the heavier steel takes time to warm up but coasts smoothly through cloudy moments. Honestly, they balance out quite well. At peak sunshine, moving 62 cubic feet of air per minute, the winning panels produced around 1,440 watts of heating power. For a simple wooden box, that is exceptional. It makes me want to test even faster fans to see where the absolute power ceiling is, but I'll save that for the next build. For my upcoming crop drying project, both the screen and the metal transpired designs are perfect. They push incredibly hot air and maintain that heat even when the fan is moving a large volume. Looking at the cloudy day data, the peak power dropped down to about 460 watts. That is roughly a third of what we get on a sunny day. It perfectly illustrates the reality of solar heaters. They are absolute powerhouses in direct sun, but you have to plan for a backup heat source when the weather turns gray. The stagnation temperatures were also interesting. You can see the heat drop the second the fans kick on, and then absolutely skyrocket at the very end of the day when the clouds finally broke. Interestingly, the bug screen maintained its lead even under the clouds. The power curves are much flatter on overcast days, proving that the amount of sunlight matters way more than how fast your fans are spinning. The overall ranking from best to worst stayed exactly the same, just with lower numbers across the board. I am completely thrilled with how this experiment played out. I learned a ton, and I know exactly which design to move forward with. In the next video, I am going to take the winning concept, build a permanent weatherproof version, and finally hook it up to a real-world application to do some actual work. That one is coming up next. This project was a blast, and I really hope you guys enjoyed the breakdown. Thanks for watching, and I will catch you in the next one.